A cosmic dial sits at the heart of reality. It isn't made of brass or steel, but of pure number, the value that determines how strong gravity is, the precise mass of a hydrogen atom. Nudge this dial by an unimaginably tiny amount, a change of 1 part in 100 billion, and the universe doesn't just flicker, it ends. Stars refuse to form. Chemistry dissolves into a bland soup. All the structure you recognize, every world, every memory, every thought, becomes mathematically impossible. This isn't a single coincidence. Dozens of these dials exist, every single one calibrated with staggering precision. The whole system looks deliberately tuned. It looks like a setup, and this places the oldest mystery of existence squarely in the cold language of physics. Who or what set these dials? That question, who set the cosmic dials, has a scientific answer that doesn't require a divine hand. It was born in a specific moment, 1973, in a crowded lecture hall in Krakow, Poland. The occasion was a symposium marking the 500th anniversary of Nicolaus Copernicus' birth. A 31-year-old physicist named Brandon Carter stood at the podium, facing the world's leading cosmologists. He adjusted his notes and began to speak. Carter had spent months wrestling with a single problem. The fundamental constants of physics, gravity, electromagnetism, the mass of particles, all appeared precisely tuned to allow life. To many, this looked like evidence of a designer, but Carter saw a logical trap. We exist, he reasoned, so we must observe a universe that allows us to exist. That seems trivial, but its implications are not. He drew a clear line between two ideas. The weak anthropic principle says the conditions we observe must be compatible with our presence as observers. If the universe were different, we wouldn't be here to measure it. The strong anthropic principle goes further. The universe must have properties that permit life to arise at some stage. One is a truism about selection bias. The other is a statement about cosmic necessity. Carter's reframing changed the entire conversation. The fine-tuning was no longer evidence of a designer, it was a selection effect. Consider a puddle of water, gazing at the hole it occupies and marveling at how perfectly the hole fits it. But the hole fits because the puddle shaped itself to it, not because the hole was designed for the puddle. In the same way, we observe a universe that fits us because only such a universe could contain observers. But here lies the hidden tension. The anthropic principle explains why we observe fine-tuning, but it does not explain why the constants have the specific values they do. The puddle analogy only works if there are infinitely many holes. If there is only one universe, then the fine-tuning remains extraordinary, whether or not we exist. Carter's talk gave scientists a way to discuss fine-tuning without invoking a designer, but it did not resolve the mystery. It sharpened it, forcing a deeper question. If the anthropic principle is the answer, then where are the other universes? And if there are no others, we are left staring at the same dials, wondering why they are set with such impossible precision. Those dials are not a metaphor. They are real, measurable forces carved into the architecture of matter. And the first one that demands our attention is the strong nuclear force, the invisible glue binding the heart of every atom. Deep inside the nucleus, protons are packed together despite their positive charges screaming to repel each other. The strong force overpowers that repulsion, holding protons and neutrons in a tight embrace. Without it, the universe would be nothing but a cloud of hydrogen and a drift of stray neutrons. No chemistry, no structure, no you. Now consider the precision required. If the strong force were just 2% stronger, a disaster occurs. Protons would bind together so eagerly that diprotons would form instantly. The early universe would have burned all its hydrogen into helium before any stars could form. No long-lived stars, no sustained energy, no planets. The entire cosmos would be a dead, still place. But if the strong force were weaker by just 5%, the opposite collapse occurs. Protons cannot fuse at all. The sun would never ignite. No nuclear fusion would forge the heavier elements, carbon, oxygen, iron, that build planets and bodies. Chemistry itself would be impossible because complex atoms require a stable nucleus, and that requires a force balanced to an extraordinary degree. This one force, whose strength is encoded in a single dimensionless number, determines whether the universe builds elements or stays sterile. And yet its value sits precisely in the window that allows stars to form, burn, and fuse hydrogen into helium, then helium into carbon, releasing energy that keeps the universe fertile across billions of years. So the strong nuclear force is not just a detail, it is a gate. The margin is roughly 2% either way. Outside that sliver, element creation stops. The elegant chain of stellar fusion, the source of every atom in your body, simply cannot happen. This is a dial set to a precision that feels deliberate. Carter's anthropic principle asks us to consider that we are simply here to measure it, and that trillions of dead universes might exist where the dial was set wrong. But we have no evidence of those other universes. We only have this one. And in this one, the strong force sits exactly where it needs to be, doing exactly what it must for the universe to be alive. The question does not fade. It only grows sharper. That sharpened question lands now, in the early 1950s, in a small office in Cambridge. An astronomer named Fred Hoyle was trying to understand how stars manufacture the elements, and he kept hitting a wall. Carbon, the fourth most abundant element in the universe, could not exist in the quantities we see unless the accepted nuclear physics was hiding something. Hoyle knew the triple alpha process. In the heart of aging stars, 3 helium nuclei, alpha particles, must fuse to make one carbon atom, but there is a catch. The first 2 alphas fuse into beryllium-8, an isotope that decays in a flash, about 10 sextillionths of a second. To form carbon, a third helium nucleus must slam into that beryllium before it vanishes. The probability seemed impossibly small, unless carbon had a special property. Hoyle calculated that if the carbon-12 nucleus had an excited state at exactly 7.65 megaelectronvolts, the resonance would act as a ladder, allowing the third helium to lock in place before the beryllium decayed. The problem, no such state had ever been observed. Hoyle bet his reputation on it. He told the nuclear physicist Willie Fowler at Caltech, if that level isn't there, you might as well abandon the idea that carbon is made in stars. Fowler and his team looked. They found the state exactly where Hoyle said it would be, at 7.65 megaelectronvolts. The Hoyle state was real. Later, reflecting on this and other impossibly tuned constants, Hoyle wrote something that haunts physics to this day. A common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology. He was a committed atheist. He did not want that conclusion, but the evidence forced his hand. Shift that resonance by less than 1%, and carbon production collapses. The universe becomes a sterile desert of hydrogen and helium. No carbon, no complex chemistry, no you. We exist only because a carbon nucleus resonates at exactly the right frequency for life. The Hoyle state gave the mystery a name and a number, but it did not answer the question. It wrote it in fire at the heart of every star. But the Hoyle state is only one instrument in this orchestra. There is another dial, set to a precision so extreme it makes the carbon resonance look like a rough guess. It lives not inside the nucleus, but in the vacuum of space itself. In the late 1990s, 2 teams of astronomers watched distant supernovae, expecting to find the universe's expansion slowing under gravity. They found the opposite. The expansion is accelerating. Something is pushing space apart. That something is now called dark energy, and its simplest explanation is the cosmological constant, a term Einstein added to his equations in 1917, then called his biggest mistake. But the constant is real. It is the energy of empty space. Here is the problem. Quantum field theory predicts that even in a perfect vacuum, virtual particles blink into existence, and this should produce an enormous energy density. When physicists calculate the vacuum energy using the standard model, they get a number. When they measure the actual value of the cosmological constant, they get a completely different number. The two differ by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. The number of atoms in the observable universe is roughly 10 to the 80th. The discrepancy between theory and observation is larger than the number of atoms in the universe squared. It is the worst prediction in the history of science. Now consider what the cosmological constant does. It governs the expansion rate of space itself. If its value were much larger, even a tiny fraction of that predicted number, the universe would have expanded so violently that matter could never clump into galaxies, stars, or planets. If it were negative and large, the universe would have collapsed back into a singularity before any structure could form. The actual value sits in a razor-thin window, small enough for gravity to gather matter, but positive enough that the expansion continues over billions of years. Without this tuning, the universe remains a featureless fog, 1 part in 10 to the 120th. That is the precision required for galaxies to exist. For stars to burn, for planets to condense, for you to be here watching this, and no known mechanism sets this number, no symmetry forces it, no deeper theory explains it. It is simply observed as if it were chosen. The Hoyle state forced an atheist to speak of a super-intellect. The cosmological constant, on its own, leaves even the atheist silent. The silence left by the cosmological constant is not a void, it is a question. And in 1973, an astrophysicist named Brandon Carter stood before a room of philosophers in Krakow and proposed an answer. He called it the anthropic principle. Carter was not a philosopher. He was a Cambridge-trained physicist trying to make sense of the fine-tuning that had haunted Hoyle and now haunted everyone. His principle, in its weakest form, sounds almost trivial. The constants of physics must allow the existence of observers because we observe them. If the cosmological constant were 1 trillion times larger, we would not be here to measure it. So our measurement of a small constant is not surprising. It is a necessary condition of our own existence. This is the weak anthropic principle, a selection effect, a filter. It is like the lottery winner who thinks the draw was rigged, forgetting that someone had to win. But the strong anthropic principle is different. It claims the universe must produce observers. Not just that we happen to live in a life-permitting cosmos, but that the laws are compelled to generate life. The weak version opens the door to a multiverse, countless universes with different constants, and we exist in the one that works. The strong version suggests a kind of cosmic necessity, a purpose threaded into reality. Yet both versions share a deeper problem. The anthropic principle does not explain the values of the constants. It only says we would not be here if they were different. That is true, but it is not a mechanism. It is a tautology dressed as an answer. To give it explanatory power, you must assume a multiverse or a universe with an intrinsic drive toward life. Neither assumption comes from the principle itself. They are added. So the anthropic principle reframes the mystery without solving it. It turns the telescope around, forcing us to look at the observer instead of the universe. And that observer, us, cannot step outside its own existence to judge. The principle is unfalsifiable. If the constants were different, we would not be here to see it. It is compatible with any observation, which makes it scientifically inert. We are left with a choice between interpretations, not an explanation. The fine-tuning remains as precise, as improbable, and as silent as before. The anthropic principle names our position in the cosmos. It does not tell us why that position exists. The anthropic principle left us with a name for our predicament, not an answer. But what if the fine-tuning itself carries a kind of fingerprint, a signature that we recognize from everyday experience as the mark of intention? Walk through a forest and find a pile of stones fallen from a cliff, random shapes scattered by gravity. That is chance. Now find those same stones arranged into an arrow pointing north. The odds of that arrangement happening by accident are tiny, and it matches a pattern it points. When you see complexity plus specification, you infer design. This is the logic behind specified complexity, formalized by mathematician William Dembski. It is how we distinguish a carved face on a mountain from a random rock formation. Now apply that logic to the cosmos. The cosmological constant is tuned to 1 part in 10 to the 120th. That is complexity, an astronomically improbable number, and it is specified. That exact value is required for galaxies, stars, planets, life. The combination of extreme improbability and a matching pattern is exactly the signal that, in every other domain, leads us to conclude design. But the objection comes immediately. If the universe requires a designer, then what designed the designer? This question misunderstands the inference. We are not claiming to have found the origin of the designer. We are claiming that the pattern in the constants matches the pattern we see in designed objects. The inference does not require an uncaused cause. It simply identifies that intelligence fits the data better than chance or necessity. Finding an arrow in the forest does not require you to know who made it. And yet, the design inference is not a proof. It is an argument from analogy. Its strength depends on how tightly you hold the analogy between cosmic constants and human artifacts. Some find it compelling, others see a leap the data does not demand. The fine-tuning remains, the pattern remains, but whether that pattern is a signature or a coincidence is still a question each of us must answer alone. But what if the forest is not alone? Imagine a foam of forests, each with its own gravity, its own laws, its own constants. In most, the stones never move, but in one forest, by blind chance, the stones arrange themselves into an arrow. Would you still infer an archer? Or would you attribute the arrow to the sheer number of forests? This is the multiverse escape. It does not deny the precision of the cosmological constant, 1 part in 10 to the 120th. It argues that if enough universes exist, even the most improbable combination becomes inevitable. We are not a miracle. We are a selection effect, the ones who happen to exist in the one universe that can contain us. String theory offers a physical mechanism. It predicts roughly 10 to the 500 possible vacuum states, different configurations of curled dimensions and quantum fields, each with its own constants, its own forces, its own reality. If the early universe underwent eternal inflation, spawning bubble universes endlessly, then each vacuum state could be realized somewhere. The result is a multiverse of staggering diversity. In this picture, fine-tuning is not a puzzle. It is expected. Most bubbles are barren, but a tiny fraction have the right constants for stars, planets, life. We live in one of those. The design inference dissolves into statistical necessity. Physicist Leonard Susskind championed this view in the early 2000s, arguing that the string theory landscape makes the anthropic principle a genuine scientific explanation rather than a tautology. But the multiverse carries a deep cost. It cannot be tested. We cannot observe other bubbles. Critics argue it is not science but metaphysics, an elegant story that explains every possible observation, which means it explains none. The arrow in the forest may be the work of an archer, or it may be the product of countless forests. Both explanations fit the data. Both require a step beyond the evidence. The fine-tuning remains. And the choice between design and multiverse remains a decision each of us must make alone. But the multiverse, for all its elegance, relies on a hidden assumption. It requires a generator, a mechanism that produces those countless bubble universes, each with its own constants, its own forces, its own laws. And that generator must be set up in a very specific way. Imagine a machine built to blow soap bubbles. Its dials are calibrated precisely. The air pressure, the viscosity of the soap, the size of the ring. If any dial were off by a fraction, the machine would never produce a single bubble, or it would produce only bubbles that pop instantly. The machine itself is fine-tuned. The multiverse generator is no different. The laws that govern eternal inflation, the energy field driving it, the quantum fluctuations seeding new bubbles, must have exactly the right properties to produce a diverse multiverse. If inflation were too fast, the universe would rip apart. Too slow, and no bubbles ever form. The dials on the generator must be just as precise as the dials inside our own universe. This is the generator problem. Philosopher Robin Collins has framed it as a trilemma. The multiverse generator, whatever it is, must be explained by one of three things. First, it could be a brute fact, a cosmic coincidence with no deeper cause, but that merely replaces one fine-tuning puzzle with another, equally improbable. Second, it could be the product of chance within an even larger multiverse, but then we face an infinite regress, each layer demanding its own generator. Third, it could be the result of design, which brings us back to an intelligence behind reality. None of these options are satisfying if your goal is to eliminate the design inference. The multiverse does not dissolve fine-tuning, it relocates it. It pushes the question back one level, but the question remains: why does the generator itself have the right properties to produce life-permitting universes? The arrow in the forest may be the product of countless forests, but those forests require a soil, a climate, a planet. And that planet itself must be improbably arranged. The fine-tuning problem did not go away. It simply changed shape, and we are still standing at the edge of the mystery, wondering why any of this exists at all. And yet, standing at that edge, we have to ask, how do we recognize evidence when we see it? What would it take to convince you that the universe was designed? In the 19th century, William Paley offered an argument. If you found a watch on the ground, you would infer a watchmaker. The intricate arrangement of gears could not have assembled by chance. The evidence seemed overwhelming. Then Charles Darwin proposed a mechanism, natural selection, that could produce complex design without a designer. Paley's evidence crumbled, not because it was disproven, but because a simpler, testable alternative emerged. Before Darwin, even Isaac Newton saw the solar system's harmony as evidence of a designer. The planets moving in perfect ellipses seemed too precise to be accidental. They required a divine mathematician. Then Pierre-Simon Laplace showed that gravity alone could produce those orbits. The mechanism replaced the miracle. This is the pattern of science. Testable mechanisms replace design inferences. But in cosmology, the pattern breaks. The multiverse is a proposed mechanism for fine-tuning, yet it cannot be tested. We cannot observe other universes. It is, by Karl Popper's criterion, not scientific. Design suffers the same fate. Both are unfalsifiable. This forces us to confront a deeper question: what kind of evidence is fine-tuning? Physicist Paul Davies has called it the peculiar impression that the universe has been rigged. But rigged by whom, or by what? The data itself does not answer. It only presents a pattern. We must decide whether that pattern points to a cause beyond nature or to a statistical fluke within a multiverse. That decision is not a scientific one. It is philosophical. It relies on prior commitments, whether you value simplicity, testability, or explanatory power. The evidence does not speak for itself. It is interpreted. And so we return to the original question, but now with clarity. The fine-tuning looks like design, but that look depends on what we accept as evidence. And that acceptance is a choice we each must make. There is no experiment that will settle it. There is only the weight of the universe pressing down on the scales of judgment, and the question echoing in the silence: what will you decide? That question, what will you decide, brings us back to the dial. We first saw it as a symbol of impossible precision. Now it represents the unresolved tension between design and chance. We have stripped away easy answers. The multiverse offers no test. The design hypothesis offers no proof. The constants remain, fixed and silent, asking for a verdict we cannot authoritatively deliver. And so the question becomes more intimate. Not what is the cause, but how will you live with not knowing? We have reached the frontier of what can be known. Beyond lies only what we choose to believe. Thank you for staying with this inquiry. If you have a path through this uncertainty, or even a feeling about it, I want to hear it. Leave a comment. The mystery is not closed. Perhaps that openness is the only honest place to be.